Hi, this video will examine how to divide one complex number by another. I strongly recommend that you see my previous video on De Moivre's theorem, which covers the theory that we will use in this video. In polar form, if we have two complex numbers, z and w, we can write each of them in polar form. So z could be the magnitude of z times cis of theta, and remember cis means cos theta plus I sine theta. And similarly we can write the complex number w in polar form as the magnitude of w cis phi. And of course theta and phi are the angles that each complex number makes with the horizontal real axis. And this is the property that we will investigate, that if we divide the complex number z by the complex number w, then the solution is the magnitude of z divided by the magnitude of w times the difference of the angles, theta minus phi. Now we can prove that property, in other words derive it from things that we already know. So first of all, let's write each of z and w in expanded form. So z equals the magnitude of z, and instead of cis theta we can write it as cos theta plus sine theta times I, and the same thing for w. There we are. We're going to divide z by w, so it's going to be what you can see here, the magnitude of z divided by the magnitude of w times cos theta plus sine theta I divided by cos phi plus sine phi I. Now to simplify this expression, we can multiply the top and bottom by the conjugate of the denominator, in other words the conjugate of cos phi plus sine phi I, which is cos phi minus sine phi I, and of course we do that to the numerator as well. And why we do that is because the denominator will simplify without the imaginary value I appearing. Now it looks a bit complicated, doesn't it? But let's persevere. So expanding the numerator, we have these terms, and expanding the denominator, we have these terms. Now in the numerator we have I squared, which is -1. That's one of the properties of imaginary numbers. And what I've done is collected the real and imaginary parts. So that term and this term are the real components. There they are. And those two. And the imaginary parts, which is that term and this one, because they both have I in it, I've combined in here. And in the denominator, again I squared gives you -1, and the two middle terms cancel out, so all we have left in the denominator is this term, cos phi, and plus sine phi, sine phi. All good so far. Now in the numerator I've just joined the real terms together. In other words, I've moved this term with this one, and we still have our imaginary terms here. And in the denominator, cos phi times cos phi is the same as writing cos squared phi, and similarly sine phi times sine phi is the same as writing sine squared phi. If you're cluey about your double angle formulae in circular functions, you would recognize that those two terms is the same as writing cos of theta minus phi, and similarly those two terms are the expansion of sine theta minus phi. Also in the denominator we have what is known as an identity in circular functions, where cos squared plus sine squared of the same angle is identically equal to 1. So we can replace that by 1. And of course, what does that leave us with? We still have, of course, all the way down the magnitude of z divided by the magnitude of w, but the 1 in the denominator now doesn't do anything, so we can leave that out. And in the numerator, you can see that this is the definition for cis theta minus phi, which is what we were trying to show over here on the top left. Alright, let's look at some examples. So in this example, first we're going to work out the solution using Cartesian coordinates. That means we're not going to involve polar coordinates, and then we'll show that we get the same answer using polar coordinates. So firstly, we have our two complex numbers. There's the top one, 1 plus root 3i, and we're going to divide it by root 3 plus I. Now the usual approach in Cartesian coordinates is to multiply, as we did in the previous proof, by the conjugate of the complex number that is in the denominator. So the conjugate of root 3 plus I is root 3 minus I, and of course we write that at the top as well. And then it's just a matter of expanding and simplifying. So just writing that in a different way. If we expand the numerator and the denominator, they are the terms we obtain. And of course expansion of two brackets, if you know your expansion process, it'll be those two terms and those two, and then those two and those two. And of course we use the same method for the two brackets in the denominator. So these are the terms we obtain. And simplifying these, firstly, I times I is -1, and of course that makes that a positive, negative times negative, and this is where this term comes from. And root 3 times root 3 is 3, and we still have the I there, and minus I, and of course root 3. And in the denominator, root 3 times root 3 is 3, I times I is -1, which makes that +1, and these two terms cancel out. So this is what we have left in the denominator. And just simplifying that now, root 3 plus root 3 in on the top, and minus I plus 3i is 2i, and of course 4 on the bottom, like that. And then just dividing top and bottom by 2, and there's our final answer. Okay, so that's working out the answer in Cartesian coordinates. Let's work out the solution using polar coordinates, using the property that we began with. So that's what we're working out. So let's call our top complex number z, and we can write that in polar coordinates, in polar form, as root 2 cis pi on 3. Just here at the bottom is just an extract from the video that I was referring that you should look at if you haven't come across this before. It just shows you the connection between the angle and the complex number. Similarly, we can write w in polar form as root 2 cis pi on 6. And now we're going to divide z by w, so this is what we're going to work out. And according to our rule, our answer will be to subtract the angle in the bottom from the angle at the top. In other words, pi on 3 minus pi on 6. And of course, we're dividing the root 2 by root 2, which cancel out, so this is what we have left. And then just simplifying, pi on 3 minus pi on 6 is pi on 6. So this is our solution in polar form. But we want to compare that to the solution we obtain using Cartesian coordinates. So let's write this in Cartesian form, which means cos pi on 6 plus sine pi on 6 times I. Cos of pi on 6, if we look at the triangle to the left, cos pi on 6 means adjacent over hypotenuse, which is root 3 on 2, and similarly sine pi on 6 is opposite over hypotenuse, which is a half. So making those substitutions, we obtain the answer that we had previously using Cartesian coordinates. This is a more elegant and more efficient manner of working it out. As a final example, this one also incorporates De Moivre's theorem. You would not try to do this using Cartesian coordinates unless you really wanted to suffer, because the first thing you would do if you did it in that way would be to expand the numerator, and expand the denominator, and that in itself would take some time. And you would do that by using the binomial expansion formula, and then you would simplify into real and imaginary, the numerator and the denominator, and then multiply by the conjugate of the denominator, and then simplify. And chances are that because the computation will be so extensive, there will be errors coming in. So this is definitely a question where you would not use Cartesian coordinates. You would use polar coordinates. So let's work it out. So we begin by writing z equals 1 minus I, and in polar form that's root 2 cis negative pi on 4. And now we want z to the power of 12, which means, according to De Moivre's theorem, that's the same as writing root 2 to the power of 12 cis 12 times the angle, and root 2 to the power of 12 is 64, and then 12 times negative pi on 4 is negative 3 pi. So z to the power of 12 in polar form is 64 cis negative 3 pi. And now let's do the same thing for the denominator. We can let w equal 1 plus I. Polar form, that's root 2 cis pi on 4. We can write using De Moivre's theorem that w to the power of 8 is root 2 to the power of 8 times cis of 8 times pi on 4. Root 2 to the power of 8 is 16, and 8 times pi on 4 is 2 pi. So now we can work out z to the power of 12 divided by w to the power of 8, which is 64 cis negative 3 pi divided by 16 cis 2 pi, and 64 divided by 16 we can work out, and our rule says that we can combine these by subtracting the angle in the bottom from the angle at the top. So that's what we're trying to work out. 64 divided by 16 is 4. We have negative 3 pi minus 2 pi, and that comes out to be 4 cis negative 5 pi. Now we want the solution in Cartesian form, so let's write that in that form. First of all, by writing it as 4 cos negative 5 pi plus 4 sine negative 5 pi I. And cos of negative 5 pi is negative 1. And sine of negative 5 pi is 0. There we are. And just simplifying that, all of that imaginary term disappears. It would be a very challenging exercise if you could perform Cartesian operations to all of that without using any form of De Moivre's theorem to obtain a final answer of negative 4. It might be worth a challenge. So until next time, please leave some comments if you enjoyed this video, or if you have suggestions for other areas of mathematics that we could investigate. Until next time, bye bye.